In this problem, we have a wide flange beam that is subjected to a shear force of 20 kilonewtons, as shown in the figure with all the dimensions. And we need to determine the maximum shear stress at that cross-section. Note that the maximum shear stress will happen at the neutral axis. And we are also asked to determine what would be the percentage of that shear force of 20 kilonewtons that is taken only by the web. So that shear force will be resisted by the flanges and the web, and we are asked to calculate the portion of the load that is taken just only by the web. Okay, the first thing to calculate the maximum shear stress at the neutral axis, what we are going to do is calculate the moment of inertia of the cross-section, because we need to apply the shear formula. And to calculate the moment of inertia with respect to the neutral axis, what we are going to do is calculate the moment of inertia of the rectangle outside the I section. So that would be the 200 millimeters width times 340 millimeters to the cube height divided by 12, and then we are going to subtract the empty spaces on the side of the web. So the width, it would be 180, the combined width of both, times the height, 300 to the cube divided by 12. The resulting moment of inertia is 250 million millimeters to the fourth. I have used this trick to calculate the moment of inertia with respect to the neutral axis of this section because the outside rectangle and these inner empty spaces all have the centroidal axis coincident with the centroidal axis of the composite section of the I section, so therefore I don't have to apply parallel axis theorem, so it's a faster way of calculating I set for the I section. Once that we have the moment of inertia, we calculate the first moment of area with respect to the neutral axis, so it's the area above or below at that level. So we have the flange. It would be the area is 200 times 20 times the distance of the centroid of that flange to the neutral axis, which is 160. And then we have the area of the portion of the web, which is 20 times 150 times the distance of the centroid of that portion of the web to the neutral axis, which is 75. So we add all these quantities and we find that the first moment of area with respect to the neutral axis is 865,000 millimeters to the cube. We put these quantities into the shear stress formula, knowing that the maximum shear stress happens at that neutral axis. So we have the shear force, 20, I'm converting it into newtons, so this is why it's multiplied by 10 to the 3, multiplied by the first moment of area, divided by the moment of inertia, and then the width over which the shear stresses are distributed. Note that we are calculating the shear stresses here at the neutral axis, so the width of the web at that point is 20 millimeters, and the resulting shear stress is 3.46 megapascals. Megapascals because I have used newtons and millimeters, so the resulting value is newtons per millimeter square. And this is the distribution of the shear stresses along the depth of the cross section. The maximum value is 3.46, which we just calculated. Now we've been asked to find out what is the portion of that 20 kilonewtons that is resisted only by the web, which is nothing else than integrating the shear stresses block over the area of the web. So basically I just have to calculate this area and multiply by the width of the web to calculate the corresponding force. To do that, what we are going to do is calculate the first moment of area at any point along the web. So let's assume that we are calculating the first moment of area at a distance y from the neutral axis. So it would be the first moment of area of the area highlighted in blue. Note that I would decompose it into the flange and that portion of the web. The portion of the web would be, the width would be the 20 millimeters times the height, which would be the 150 minus y. and then the centroidal distance to the neutral axis would be given by this value. So I'm just going to write a formula for the first moment of area at any arbitrary point located at a distance y from the neutral axis, where y is going to vary from 0 to 150 millimeters. And this is what I have here. So you notice that the first moment of area is a function of y, and I could plot any value of y, I would obtain the corresponding first moment of area. Now I'm going to calculate the corresponding shear stress at any point y. So I have the shear force, the 20 kilonewtons multiplied by 1,000 to convert it into newtons, multiplied by the first moment of area at that arbitrary point at a distance y from the neutral axis, and then divided by the moment of inertia that we have previously calculated, and the width over which the shear stresses will be distributed. We are just talking about the web, so that width is constant and is 20 millimeters. So I end up with an expression for the shear stress at any point along the web that is a function of that distance y. So if I want to calculate the force taken by the web, all I have to do is multiply this shear stress times the area over which is acting to calculate the force. So this is what I have here. So the shear force at the web, I'm multiplying by 2 because when I calculated the first moment of area, I was just considering half of the web. And then note that I'm multiplying the shear stress times a differential area and varying 0 to 150 because my variable of integration is going to be y. So that means that I have to write dA as a function of y, which is the width of the web times dy. So I end up with a simple integral, definite integral, and when we integrate from 0 to 150, we find that the corresponding force is 18.95 kilonewtons, which is almost 95% of the applied load of 20 kilonewtons. So what we can see is that the web is the main contributor to resisting that shear force, and then the top and bottom flanges will be carrying the remaining 5%.